Hey everyone, welcome to another explainer brought to you by Forge College. Today, we're crossing a pretty massive threshold in our Programming with Solana track. We're diving deep into advanced template customization, and we're going to tackle something that literally every Web3 developer has to master, and that is modifying program logic and adding features. Basically, we're taking all that theory and turning it into a working, strictly engineered reality. Let's get right into it.
So to really understand where we're going, we kind of need to remember where we've been, right? Think of this whole process like an engineer's blueprint. In our last lesson on customizing input parameters, we essentially installed this shiny, brand new dial onto our machine. And hey, it looked great. The validation rules works perfectly, and it absolutely wouldn't let users input out of range values. But right now, that dial isn't actually connected to anything. So today, we're taking off the casing, grabbing our tools, and wiring that dial straight into the machine's engine. We're modifying the program logic so the smart contract actually does something with those new inputs.
To safely implement these new features, we're going to follow 6 strict engineering phases. First, the blueprint. Second, designing the instruction. Third, writing the logic. Fourth, quality assurance. Fifth, a client demonstration. And finally, takeaways and next steps. All right, starting off with phase 1, the blueprint. Let's look at the exact account and parameter specs.
Before we even think about writing a single line of code, we need exact specifications for our new instruction, which we're calling ApplyMultiplier. It's going to read a numeric value, multiply it by our parameter, write the new result, and then log the event. Now, looking at this engineering spec sheet, you can see we've got 3 distinct components. First, the state account. This holds our numeric value and, crucially, it must be writable. Second, the authority. This is the signer authorizing the mutation. And third, our parameter, which is the unsigned 64-bit integer multiplier. Getting these roles wrong, especially forgetting the authority signature, is honestly a brilliant way to just let completely unauthorized users mutate your state. And trust me, having to explain that makes for a very, very bad day at the office.
Moving on to phase 2, designing the new instruction by adding a brand new variant. So, we're opening up our instruction module and safely adding ApplyMultiplier as a new variant to our existing template instruction enum dispatcher. Why do it this way? Well, by adding a new variant rather than messing with the existing ones, we keep our client interaction contracts completely stable. Older clients that don't even know about this new multiplier won't suddenly just break because their deserialization rules remain completely untouched. It's backward compatibility by design, and it's a real saver. But hey, before we wire this up to our core logic, we absolutely have to talk about safety. Specifically, mathematical safety. We'll be using something called checked arithmetic. See, when you multiply two 64-bit integers, there's always a risk that the result will exceed the maximum allowed value. If we just use standard math operators, our Rust program might silently overflow or, worse, abruptly panic and crash. So we use helpers like checked_mul because, well, we don't want our machine exploding. We want it to catch the overflow and return a graceful descriptive error code right back to the client. Phase 3, writing the program logic. Let's look at the instruction handler. All right, now we're stepping onto the factory floor, where we actually process the instruction, mutate the state, and, perhaps the most challenging part of all, keep the Rust borrow checker perfectly happy. We tame the sheer complexity of on-chain logic by breaking our handler down into 5 isolated blocks. First, parse the accounts from the incoming transaction. Then perform basic security checks to confirm the signers. Next, deserialize the raw data into a usable Rust struct. Fourth, perform our safe computation. And finally, log the event. It's neat, it's safe, and it's highly readable. Let's zoom in on the engine block itself, which is step 4. We pass our current state value and our multiplier directly into our checked_mul helper. If it succeeds, great. But notice that map error tacked onto the very end? If our math fails, we map that failure directly to a custom program error. This ensures our whole mechanism is completely deterministic. A failure isn't some chaotic crash. It's a predictable, documented error state that any client can easily read and understand.
Okay, phase 4, quality assurance. It is time to run some unit tests.
As good engineers, we literally never ship without running unit tests. The true beauty of separating our logic like we did is that we can test it instantly without having to deploy to a live network. By just running a simple cargo test, we spin up some mock runtime state, call our processor directly with our mock accounts, and assert that our state updates exactly as expected without any panics. Seeing those green passing tests?
That means your core logic is fundamentally sound.
But what if you do get an error? Triage is an absolutely vital engineering skill. If things fail, step 1 is to rerun your unit test to isolate whether the bug is in your Rust logic or your client side. Step 2, sprinkle in some MSG logs to trace the execution path. Step 3, verify account ownership and rent exemption. And finally, check your serialization. I can tell you from personal experience, if you're staring at a nasty borrow checker error or a random panic, it's almost always because you messed up a borrow_mute call or your client and program just completely disagree on how to serialize the Borscht data.
Moving right along to Phase 5, the client demonstration. This is our end-to-end test.
Once those unit tests pass, we need to prove our code actually works in a real-world transaction flow. To do this, we open up our terminal and run Solana test validator-reset. This spins up a localized, fully functioning Solana blockchain right on our own machine. We then run a minimal TypeScript or Rust client script that creates the state account, constructs the exact serialized ApplyMultiplier instruction, sends the transaction, and then fetches the resulting account data.
And if everything is wired up perfectly, you fetch the account and you see this. Imagine our initial state was 3, and we passed in a multiplier of 5. Seeing 15 printed right there in your terminal is honestly the ultimate victory. It proves our end-to-end logic, from the client construction, across the network, into the deserializer, through the checked math, and all the way back into the state, is executing flawlessly.
Finally, Phase 6, takeaways and next steps. Let's quickly review our architectural principles.
We've successfully built a feature, but let's really lock in the engineer's credo for Web3 development. Separate your concerns. Keep your parsing and validation right at the input boundary. Isolate your pure logic, like those math functions, into highly testable, distinct modules. And confine your account deserialization and state rights exclusively to the handler. Trust me, following this strict separation makes testing, debugging, and scaling your programs exponentially easier down the road. Now, before you clear your workspace for the day, a quick piece of advice. Save your artifacts from today. Keep the branch with your new feature, save your client scripts, and seriously, even save any failing test outputs you bumped into. Because in our very next lesson, we're going to dive deep into debugging custom templates. Having a reproducible client call is going to be your absolute best tool for tracing transaction execution logs.
I want to leave you with this final kind of provocative thought. You've built a pristine, perfectly functioning machine in the absolute safety of your local environment. But if your machine behaves perfectly locally, how exactly will you track down silent state mutations when it finally faces the chaotic, totally unpredictable runtime conditions of the live network? Well, that is exactly what we'll be exploring next time. This explainer was brought to you by Forge College. If you want to master these Web3 engineering topics and get your hands dirty with some real code, head over to forge.college to learn more. Thanks so much for watching, and keep building.